some examples here. So first of all, multiple choice question. So when you take a look at this multiple choice question, you have a function that's giving us sine x plus cosine x. Which of the following expressions, again, what they want us to find here is they want us to find the average rate of change over this particular interval from 0 to pi. So this is where you're simply going to use your slope formula, your f of b minus f of a all over b minus a. So this is your average rate of change. So again, remember that close interval 0 to pi, those are your x values. So again, I'm going to plug in my values into this formula. So f of pi minus f of 0 all over pi minus 0. So which would be your correct answer choice? C. Okay. So any questions on if they asked us, again, they're not asking us to actually calculate what that average rate of change is from 0 to pi. They just want to see the setup. So any questions on that one? All right, let's take a look at another one. All of you go ahead and try this next one on your own. Again, they're still asking you to calculate the average rate of change over your interval from 1 to c, but they're also telling you what that average rate of change is, that 0.25. So go ahead and try that one on your own. So what answer choice did we get for this next example? D, very good. So are we comfortable? Are we okay? Again, this is the algebraic approach. Algebraically, are we okay finding the average rate of change? The questions on that one. All right, let's take a look at a graphical approach. So we have a graph of some function, and then when they give us this inequality that they're saying that f of b is greater than f of a, remember this is a y value. These are just comparing your y value. So they're telling you that this y value, whatever it is greater than this other y value. And again, they're giving us a closed interval going from a to b. So again, I've got this closed interval going from a to b. So if you want to change that into bracket or interval notation, be my guest. So this is your closed interval. They're telling you that the derivative exists for all x except at x equals 0. We'll talk about why that derivative does not exist at 0 in a few minutes. So they want to know for how many values of c. Again, c would be an x value because remember a and b are your x values, where the limit as x approaches c of f of x minus f of c all over x minus c is equal to f of b minus f of a all over b minus a. Huh? What are they talking about? Well, what is this right here? We just had two examples. What does this part calculate? This part calculates your what? It's the average rate of change. So that tells me the average rate of change. So as I mentioned when we were talking about the average rate of change, graphically, what is your average rate of change? That is simply the slope of what? The slope of your secant line. So really what this is when you're looking graphically, you're looking at the slope of the secant line. Does that make sense to everybody so far? So if I was to actually sketch my secant line, my closed interval again is going from A to B. So I would draw a line connecting those 2 points. So again, this is my secant line. So now the next question is, well, what am I checking to see what it's equal to? What is this limit as x approaches c of f of x minus f of c all over x minus c? What does that actually calculate? It's the instantaneous rate of change, or it's the derivative. It's my f prime. And graphically, what is your f prime? Your f prime is what? The slope of what? Tangent line. So in essence, what this question's asking you is how many times will the slope of your tangent line be equal to the slope of the secant line? Or another way they could have asked this is how many times in this interval will your instantaneous rate of change be equal to your average rate of change? So a couple different spins and twists and turns that they can put on this particular problems involving rate of change. Again, so this is a graphical approach. So anytime they're talking about average rate of change or instantaneous rate of change and they're giving you a graph, you're looking at slope of tangent lines and slope of secant lines. Okay, does that make sense to everybody so far? So this is kind of a visual. Again, you may want to take a straight edge or whatever. So really what we're trying to do, again, is I would take my pencil and kind of slide it down. Oops. Oh, I just did there. And estimate approximately how many times could I sketch a tangent line and have it be equal to the secant line. So again, so this is the approximate slope. So as you can see, there's probably going to be one time right about, let's say, right about here. Wouldn't you agree with me that that would probably be approximately equal to this? Actually, not quite right there. Let me erase that. It's a little too steep. Probably right about here. Would you agree with me that the slope of the tangent line would be approximately equal to the slope of the tangent line? See if you can find any other places for me. Sometimes it's helpful to kind of maybe take like a straight edge or take the cross inner covers and again, line it up below your secant line and then slide it down in the graph to see approximately how many times. Sometimes that's helpful too. Remember, they already told you x equals 0, it's not differentiable, so we cannot have an instantaneous rate of change of 0. How many did you find? I found 4. I found 4. So I found one right about here. I also found one right about here. And then probably right about here. So about 4 times. So not exact spots, but again, questions will ask you approximately how many. Does everybody see that now, where it's 4 times? Okay. Like I said, sometimes it's helpful to kind of take a straight edge and kind of slide it down. Say, oh, it's going to be right about here. It's going to be right about there. And then again, look over here. Right about here. And then right about there. That's on the stuff. Okay. So any questions graphically on how to find? So this question, like I said, when they ask questions on AP exams or AP type like questions, they're not straightforward. They're not straightforward. They want you to make sure you recognize that that one is your average rate of change. They want to make sure the other one is equal to the instantaneous rate of change. And they're recognizing graphically. So it's actually asking you quite a bit in terms of what does this represent. And again, tying it back to the slope of the tangent line being equal to the slope of the secant line. All right, let's take a look at another example. So similar type of question, it's a graphical approach. Here again, they're telling you that f of b is greater than f of a. I think that's a typo, that should be less than. You can clearly see that f of b is less than f of a. Again, we have this closed interval going from a to b. Again, they're telling us that the derivative exists for all x in the interval, except where x is equal to 0. For how many values of c does, again, that limit as x approaches c, again, remind me again, what does this represent? That represents your what? Derivative. So we know that's the derivative, which I know is the slope of the tangent line. Again, remind me again, what does that represent? Slope of the secant line. I know that's my average rate of change. Just abbreviating rate of change there, which is again the slope of the secant line. So again, you want to sketch your secant line, which is right here. So see if you can do that one for me. Again, this is your secant line. So again, see if you can find how many times does the slope of your secant line equal the slope of that tangent line. So I came up with about 3 times. Probably 3 times. I kind of sketched them of where they were, approximately where they were. Actually, this one should probably be a little bit further up this side, but any other questions on that? Okay, so we've been looking at definition of the derivative, having you recognize when giving you the definition of the derivative, having you recognize what is your f of x, what is your x value that's plugged in. Again, remember we talk about instantaneous rate of change. That instantaneous rate of change, like I just mentioned, is the slope of your tangent line, which is the derivative of a function. So there's 3 different words that they can use all to represent the same animal. Instantaneous rate of change, slope of a tangent line, or derivative of a function. All the same value, calculated the same way. And again, when we talk about the definition of the derivative, this is what we've been looking at for a couple class periods now. Remember, there is that second definition. This one right here. The difference between those 2 definitions, if you were to actually use those definitions to calculate the derivative, this second definition would just give you a numerical answer. You would just get a number as an answer. This first definition is the one that's more common because it's a little bit more powerful, because this will actually give you the derivative as a function. You'll actually get an equation and you'll get a function out. So that's really the difference between those 2 definitions. So let's take a look at this example here. State the derivative of the function using derivative notation. It's not actually asking you to actually work it all the way out. But again, what you're going to do is use this first definition. We're going to use that limit as h approaches 0 of f of x plus h minus f of x all over h as it relates to this particular function here. So first of all, before you can set up the derivative notation, there's 2 things you have to know to substitute into this formula. Number 1 is you have to know f of x, which I know, they're giving that to me. The second thing you have to know is you have to know the f of x plus h. Now remember, function notation. What is x plus h? X plus h is your input. That's what you put into the function for x, correct? So what you're doing is you're taking your x out of this equation and you're just replacing it with the x plus h. So all I'm going to do in this equation is take out my x and replace it with my x plus h. make sure you leave parentheses around that x plus h. Because it follows that subtraction sign. So this is my f of x plus h. Okay. Any questions? So it's just your function notation. You take out the x and you replace it with that x plus h. So I have that x plus h to the second minus, make sure you leave parentheses around the x plus h, and then the plus 1. Yes, Alan.
Earlier this week we went over like the 2 different forms
Mhm.
of limits, because you can approach 0 or you can approach a number. Are we always going to use the limit as it approaches 0? Or
Yes, typically that's the one that's more commonly used.
Okay.
Because you get that function answer versus just a numerical answer. So now we're ready to go ahead and take my f of x and my f of x plus h and plug it into the definition of the derivative. So the limit as h approaches 0. So my f of x plus h I found to be x plus h to the second minus the x plus h plus 1. Remember, all of this right here, all of this is my f of x plus h. Minus. Again, it's following a subtraction sign, open up a set of parentheses. Your f of x. Remember, your f of x is the original equation. And it's all over h. And that's all you need to do using the derivative notation. So through all of this is your final answer. Okay. So the trick is, before you get started with that definition of derivative, identify f of x, which again is just your original equation, and then identify your f of x plus h. Take out that x and replace the x plus h in it. So any questions on that one? All right, you try one. Go ahead and try this next example on your own. This is what you should come up with when you express that with derivative notation. All I had to do, again, your f of x plus h, remember, was just taking that original equation, taking out the x and replacing it with that x plus h. Okay. Last year, I think your pre-calc teachers tortured you a little bit, made you simplify, work it out all the way algebraically and find it. And then all of a sudden they showed you all those shortcut rules to make you appreciate the shortcut rules, because sometimes even though they're shortcuts, they don't seem like shortcuts. So I always say to my students, I said, remember, it could be worse. You could be using that definition of derivative again. So as bad as you may get at quotient rule and all that other stuff, remember, it could be a heck of a lot worse. You sometimes forget that those are the shortcuts. Questions on the definition of the derivative? So now maybe when you look at those problems we were doing earlier, you can recognize maybe a little bit easier, oh, this is my f of x plus h. Because sometimes what they'll do is they'll actually plug in a number for x, which is a lot of the problems we were actually looking at as well. All right, let's take a look now at graphically. So I had you sketch when we were looking at trying to find where the slope of the secant line is equal to the slope of the tangent line. How can you graphically find the derivative of a function? So again, we know that the derivative graphically is the slope. So it all goes back to algebra 1. Remember, slope is rise over what? Run. It's your y2 minus y1 over x2 minus x1, going back to your basic slope formula from algebra 1. It's also what we call, remember, the change in y over the change in x. And I don't know if your algebra 1 teacher showed this to you, but there is a Greek symbol to express the change in y over change in x. That's your delta symbol. It looks like a little triangle. So you can also express it as delta y over delta x. That delta means change. So really, when you're taking a look at a graph, now I've sketched the tangent lines for you. If I want to approximate, and again, these are going to be estimations, the derivative of the function at each particular point, what you're going to do is you're going to choose two distinct points on your tangent line. So find 2 points on your tangent line and then use that to find the slope. So for example, f prime of 1. So right here on the graph, here's my point where x equals 1. So I've already sketched the tangent line for you. So what I want to do is I want to pick a point also on my line. And then I want to calculate the slope of that line. So for example, my rise, when I count up, that's going to be 1, 2, 3, 4. So my rise is going to be 4. Did I count that right? Let me just see. 1, 2, 3, 4. And then my run, when I go to the right, that's going to be, I count over 1, 2. So 4 over 2 is going to give me approximately a slope of 2. So any questions on how I can approximate the derivative given the graph? Go ahead and try B for me. Everybody come up with -4? Don't forget when you go down, that's a negative direction. Also, remember what's your other negative direction when you have to go to the left. Okay, so that's how, so now you know how to do derivatives all 3 ways, algebraically, from a table, and now from graphs. All right, so a lot of times, however, they're not going to actually sketch the tangent lines for you. So for example, a lot of times they'll just give you some graph and they're going to ask you to estimate. Again, these are estimations, reasonable guesses, reasonable estimations. Again, what I always tell my students is do a comparison with a line that's 45 degrees to the horizontal. When you have a line that's 45 degrees to the horizontal, I always call that a slope of 1. So think about what's happening. The closer a line becomes horizontal, what's happening with the slope in comparison to 1? It's getting what? Smaller and smaller. It's approaching what? 0. Versus the other way, I know vertical lines have what kind of slope? Undefined. So as the slope is getting steeper and steeper, as it's approaching more vertical, the slope is getting what? It's getting larger and larger, isn't it? So that's what's happening. So kind of keep that in the back of your mind. So when you take a look at these graphs, they want you to estimate the derivative at -5. So what I always do is sketch a small tangent line. Again, these are reasonable estimations. Compare it to that 45-degree with a horizontal. What do you think about this slope? Is it going to be greater than 1 or less than 1? Less than 1. We all agree with that. Is it going to be positive or negative? Positive. It's all positive. So what would probably be a reasonable approximation? You want to extend this out. Maybe I go out, up 1, and then over 2 or 3. So what would be a reasonable estimation? 1/2 or 1/3? 1/2 is reasonable. 1/3 is reasonable. Okay, reasonable estimations. See if you can do the next 4. By the way, is that derivative going to exist at x equals -1? No, why not? Sharp turn. We're going to review differentiability in a few minutes, but again, just to, how come f prime of 4 is undefined? Vertical tangent. Again, we're going to talk about more about differentiability here in a few minutes. What about f prime of 6? 0. Exactly. Horizontal tangent lines have a slope of 0. So now you should be able to do derivatives all 3 ways. We've been practicing them algebraically. We've been doing them from tables, and now we've done them graphically. So any questions on derivatives graphically? Okay, I figured I'd type up the directions for the calculator stuff, so I'm not going to spend a lot of time going through this. Just a couple things and a reminder with the calculators that we wrapped up this morning. Remember, anytime you're dealing with trig and calculus, you are in radian mode. Okay, so this is the directions I've been going over with you in terms of finding the derivative. So those are your calculator instructions that we've been doing. So go ahead and practice to make sure you're comfortable. Go ahead and try practice 3B for me. See if you can use your calculator to find this derivative, natural log of 5x plus 7. So if you remember from last year, 3 conditions have to happen in order to be continuous. The limit as x approaches a from the left has to be equal to the limit as x approaches a from the right, which is equal to your defined value. Remember, there's 3 types of discontinuity. So if a function gets discontinuous, it's one of 3 things will happen. Number 1, we have what's called removable discontinuity. Removable is when you have a hole in the graph. When you're checking algebraically for continuity, this is how you know it's removable. It is because your defined value is not equal to your limit, either from the left or from the right. Or it may also happen that f of a doesn't exist. A might not be in the domain of the function, so therefore it can't be continuous there. So that's removable. The second type is actually a category of non-removable, and that is your jump. Where your graph doesn't connect. This happens when the limit as x approaches the right does not equal the limit as x approaches the left. So it's considered non-removable discontinuity, but a more specific name is a jump. So a jump discontinuity is non-removable. Sound familiar a little bit? Little bit? Sam said I better shake my head because Mrs. Berge will probably come over and yell at me if I don't. I'm keep teasing Sam. Another type of non-removable is your infinite. still part of the category non-removable. This is when you have a vertical asymptote at that particular X value. So A is going to be undefined, but it's not a whole. You've got a vertical asymptote. So those are your three types of discontinuity. When you talk about differentiability, for a function to be differentiable, the limit of the derivative from the left has to be equal to the value of the derivative from the right. So you take the derivative of f of x and you check to see what's happening on the left and to the right, and make sure it's the same value. Just like there's three ways to be discontinuous, there are also three ways for a function not to be differentiable. So the three pictures you see down here are three examples of where you do not have differentiability at 0. So first of all, as we saw in some previous graphs, if you have a sharp point, or they may also call that a cusp. So the absolute value function, as you see in this first graph, it's not differentiable at the vertex. The reason why is because the value of the derivative from the left is negative, but the value from the derivative on the right is positive. So those two derivatives are not equal at x equals 0. So the derivative from the left does not equal the derivative from the right. That's what causes that sharp point. So you could also have a, discontinuous. If you know it's not continuous at a certain x value, it is not differentiable. So if you have a hole, you have a jump, you have a vertical asymptote, it's not differentiable there. And then finally, if you have a vertical tangent in the graph. So right there, you can see it. Questions on what makes it not differentiable or not continuous? So just a couple things to remember when you're talking about differentiability and continuity. If it's told to you that it's differentiable at a point, then you know that it's also continuous. So if you know it's differentiable, it has to be continuous. So again, remember, differential does imply continuous. However, the converse is false. Just because you know it's continuous does not mean it's differentiable. And I always tell my students to drill into your mind, the absolute value function. That proves that point. Your absolute value functions are continuous for all real numbers. However, it is not differentiable at the vertex. So I always tell my students, drill in your brains that absolute value function to help you if you ever get confused which one is which. Differentiability, we know it's continuous. However, continuity does not mean differentiability. And your absolute value function can prove that to you. Your contrapositive is true. In other words, if it's not continuous, it can't be differentiable. So right away, you know if it's not continuous, it's not differentiable. They love to ask questions like piecewise functions about continuity and differentiability. So here's an example of your piecewise function. So determine whether it's continuous and differentiable. When you're asked about continuity and differentiability, always check for continuity first. So check to see if it's continuous first. Because if you find out it's not continuous, you can stop, you know it's not differentiable. So remember to be continuous. Well, first you have to decide what are my candidates where discontinuity could occur. Look at your functions in the piecewise function, 5x to the third. That's a polynomial. Are there any holes or jumps or asymptotes in 5x to the third? No. 2x is just a what? Line. Are there any holes? Are there any gaps? No. So I know that both the functions are continuous for all real numbers. So if this continuity is going to occur, it's going to occur where the domain is restricted. Do you agree with that? Because we don't know, this piecewise function may not connect. So while we have to check for continuity is we have to check at x equals 0. There are no other candidates. Any questions on why I'm checking 0 and nowhere else? So remember the definition of continuity then, f of 0 has to be equal to the limit as x approaches 0 from the left and has to be equal to the limit as x approaches 0 from the right. So that's your definition of continuity. All you're doing is plugging in zeros. Don't make it harder than what it is. You're just plugging in zeros. So how do I find f of 0? Where do I plug 0 into, the first or the second part? First. So 5 times 0 to the third is just going to give me what? 0. This also tells me what? When x is less than or equal to 0, this is also telling me the limit as x approaches 0 from the left. Remember what I say from the left? We're talking about x values less than 0. So I also know that the limit as x approaches 0 from the left is also 0. So far, it's looking good. So the last thing I have to do is find the limit as x approaches 0 from the right. So I'm going to plug 0 into the second part of my piecewise function, so 2 times 0, 0. So is this function continuous at x equals 0? Yes. Can I automatically assume it's differentiable? No. So to now check for differentiability, first of all, you want to find f prime of x. So I'm just going to take the derivative of each individual function in the piecewise function. So what's the derivative of 5x to the third? 15x squared. What's the derivative of 2x? 2. So then to be differentiable, what has to happen is the limit as x approaches 0 from the right of f prime of x has to be equal to the limit as x approaches 0 from the left of f prime of x. See if it is. What do you think? What do you think? No. Because what's the derivative as you're approaching 0 from the right? That's just 2. From the left, that's going to be what? 0. So again, 0 does not equal 2. So therefore, it's not differentiable. So what's happening when the derivative from the left is not equal to the derivative from the right, that's creating a sharp turn or sharp corner in the graph. So that's what's happened. That's creating that sharp turn. So that's what happens when those derivatives are not the same. How would I know I had a vertical tangent? Well, what kind of lines have, what do vertical lines, I can't even get that. What is the slope of a vertical line? Undefined. So if you were to find this derivative and plug in a number and you got undefined, you know you'd have a vertical tangent in the graph. Okay. So any questions on that one? So any questions on how to check for continuity or differentiability? See if you can do this example for me. It's multiple choice. Which of the following statements is true? So really you have to check for continuity and differentiability. Remember when you find your f of 5, so f of 5, remember, is 2 times 5 minus 4, which is 6. But when I find the limit as x approaches 5 from the left of f of x. Remember, when you're trying to find the limit of a constant, it's just that constant. So therefore, these two are not equal. Right? Now I'll do it graphically. Go ahead and take a look at the graph and tell me what's happening at each of those particular x values.